Okay, so welcome back. So in my previous video, I did logic gates, and we also covered things like the main gates, like the AND gates, OR gates, and NOT gates, right? We also covered a few combinational logic gates like the NAND and the NOR. We also looked at a few truth tables. So in here, in this session, we are going to cover a Boolean algebra. Okay. So in Boolean algebra, now I have put a few of the common Boolean algebra rules. So this is, for example, the rule. So we are not going to prove any of these rules, right? So if you want, you can do the simple truth table, and then you can see that the rules work, right? So here in the AND gate, we have A and A is equal to A and not A equal 0. So we can use this in a truth table, and we can identify that these things can be validated accordingly. Now, the thing is, we are not going to validate these AND gate rules or the OR gate rules or even the absorption rules. So these are called absorption rules. So some of these are De Morgan rules. So there are ones like the A plus B naught or A plus B bar is equal to A bar multiplied by B bar. Okay, so we are not going to do we are not going to prove it rather, but we have to memorize some of these rules, if not all of them, right? So because they are Boolean algebra, they are not normal algebra, but they are considered Boolean because the values of this is either 1 or 0. So it's either true or false, right? It is not like, numbers like, 1, 2, 3, 4, where you can multiply 3 by 3 and get 6. Okay, so this is not like that. When it comes to AND or logic gates, right? A multiplied by A, so that's basically A and A. So that's like, for example, 1 and 1 is equal to 1, right? So because it's an AND gate, both conditions need to be satisfied in an AND gate. That is why in an AND gate, A and not A is 0, because 1 and 0 is definitely is 0 in an AND gate, right? Here's another one. A and 1. So in an AND gate, you send A as 0, it's going to be false at the end, because 0 and 1 is 0. So that means A is 0, therefore you can put A here. So if A is 1, A will still remain as 1. So in this AND gate, you will get back the value that you put in at the very beginning as the input value. So the output value is equal to the input value if the second input value is 1. So if the second input value is 0, the output will be always 0, regardless of A's input, right? Because 1 multiplied by 0 is always 0, right? So we are not going to prove any of this. You can download one of my notes, in which I will add it to the link, and you can download that the notes. It contains the entire Boolean algebra expressions, the rule sets, including the gates, and also some exercises that you can do. So let's start with a few Boolean algebra expressions. Now, since you have not memorized the Boolean algebra rule table, I have put in the rule table here, right? And we can refer them whenever we want to. We'll even put in a truth table to see how it works, okay? Right, so how do we simplify this expression? F equal A bar plus B multiplied by A plus B. So I'm looking at this in from an angle of logic gates, right? So from that particular angle, I know there is a NOT gate and there is an OR gate. Okay, so a NOT plus an OR gate. That is why you have this plus sign. So there is two components here itself, right? Then we also have another OR gate on this side. So that's another one component. And we also combine these two with an AND gate. So that's altogether four components that you're looking at in this algebra, right? So let's simplify this now. Okay. So standard algebra rules also apply. So that's A bar multiplied by A. So that's A bar multiplied by A plus A bar multiplied by B plus BA plus BB. Right, now we can look at the tables down here. So the Boolean algebra table shows me that A into A is A. So therefore I can see that B into B is B. So let's look at the one over here. A bar into A is 0. Okay. A bar into B. So that's A bar into A is 0. A bar into B. So A bar into B is still A bar into B. That cannot be changed. Plus A B. So BA is still AB. There is no difference from in that. Okay. So now I can take out the B. Okay. I'm going to take out the B, which leaves me with A bar plus A. Standard algebra rules plus a B. Now A bar plus A is an OR gate, which is here. So you can see A bar plus A, which is 1. So this is B 1. So B into 1 is still B. B plus B, here we can see here it's still the same because it's an OR gate. So B is the final output. Okay, so B is your final output in this. So all the others basically are simplified. Now the reason why we do this, okay, the most important reason that we learn Boolean algebra is to minimize the number of logical steps in a microprocessor. Right? So if you have a microprocessor and you have all the circuits, the transistors that are going through, say, remember, every single transistor is basically a logic gate. So the objective is not to have highly complicated rules like this. So if you have lots of, rule sets like, if conditions and, case conditions and for loops and all that, and you want to control basically of that, but you want to put it into an actual hardware device, right? You have to have a minimum number of transistors. You can't just, put all of these transistors. Look at the amount of logic gates here, right? There is already 1, 2. Okay, there are way too many logic gates. Even I can't count the number of logic gates here. All of these logic gates can simply be simplified into just B. That's it. The input of this entire combination of logic is just translated into B. So therefore we can get rid of all of these logic gates. See? And just come. That's the whole idea. So you get performance from your microprocessor, less heat generation, less power consumption, and your microprocessor is going to be much, much smaller, which means you can pack more logic into your microprocessor. Now, today's microprocessors has over a billion transistors, not million, it's over a billion transistors in these microprocessors. So that's the whole idea, is to reduce and simplify the number of transistors that are in here using Boolean algebra. Okay, right. So let's look at the next question. Right. Now, if we look at this one, we can simplify it by taking, let's say, the common value from here. So the common value would be from here. Common value would be b. Now, if we take the b out, what's going to happen is we'll have b with, a plus c. Now, the problem here with a plus c is it doesn't make any difference whatsoever. We have not really simplified this, right? So I'm not going to do it that way. I'm going to look for something else. Maybe, here we go. Let's look at it from this side. BC and BC. Okay, so definitely there is something that I can do from here. So I can take the C out, right? And then I can put here B plus B bar. Now, B plus B bar is always equal to 1, right? So that's AB plus C plus B bar. So that means this is going to be a C. So that's A, B plus C. So that's AB plus C. That's the simplified answer. Okay, so let's look at our next equation. So before we look at the next equation, in case you're looking at this still and wondering how I got B plus B bar, we can see it from down here. The A plus A bar is always equal to 1. So therefore B plus B bar is still equal to 1. If we draw a logic gate for this, right? Now in Boolean algebra, that's a plus means OR gate. So if I draw an OR gate there, and right, the two inputs B plus B bar. So B plus B bar is basically, let's say if this is 1, this is 0, right? That means this will be 1 because this is an OR gate, right? One of these has to be true for this to be true. So if we even shift, let's say B to 0, B bar would simply mean 1. So let me put 1 there. Okay, so again, this will always equal to 1. That's how we get this value of 1. So it basically, that is an OR gate. That is how we get 1, and then C multiplied by 1 is still C, and the AB still remains. Okay, let's look at another example. Right, now in this one, in this particular expression, I think there's a little more levels that you need to go through. So it's simple, but you still need to follow a few more steps in order to get to the final expression. So let's simplify this logic. So here we have A bar B bar. So sorry, A bar B plus AB plus A bar B bar plus BC. Now we can simplify these two. Why would I want to simplify these two? Because I can see if I take the B out, I will have A plus A bar. Now I can simplify the a plus a bar as 1. So it's over here. You can see it down here in the Boolean algebra. In the table, you will notice that a plus a bar is 1, or b plus b bar is 1. So therefore, I can take the b out. So what I'm left is a bar plus a. And I know that a bar plus a is equal to 1, right? I'll leave the rest the way it is because they need to be simplified later. Right, so we have b bar plus, sorry, it's not b bar, it's b plus a bar plus b bar plus bc. Okay, so we have that. Now what we can do is we can do something like this. Since we already have this, we can take the b out from here. Okay, we can take the b out from here. So I'm going to simplify, I'm going to combine these two. I'm going to take the common value from this b1 and bc. I'm going to take the common value. So when I take the common value b out, I am left with 1 plus c plus this remaining a bar b bar. Okay, a bar b bar, right? And from here I took the common b out, so which means I'm left with c. So here we go. Right, so now c plus 1 we have here. Here we go, we have in the Boolean algebra table a plus 1 equals 1. So a plus 1 equals 1, that means c plus 1 equals 1. So here we go again. B is actually again 1 plus a bar b bar. Right, so we are now getting to the final step. Okay, look at this. B plus a bar b bar is here. It's an absorption rule. It looks very similar to this. See, a plus a bar dot b, right? So it looks like, right, this absorption rule is ignoring the a, the duplicate a, right? So you have a plus b being the final result. It looks like, you know, this a is ignored, okay, but the b is preserved. A is completely ignored, so even if it's bar, it's ignored, right? So what's going to happen is this expression here is going to become b. We can ignore this one because b multiplied by 1 is still b, right? Plus a bar b bar. What's going to disappear is this b bar, and what you are left with is a bar. So this is the final output, b plus a bar, or rather a bar plus b. That's a much nicer way of putting it, right? So now that you know how to play around with Boolean algebra using, you know, the AND gates and the logic rules, especially the absorption rules and De Morgan rules, etc., I have created an entire document. You can download that document and you can start practicing creating your own algebraic equation, right? So now if you have gone through the internet and check some of the videos out on Intel Core microprocessors, you will notice that there is a new microprocessor out called the Core Ultra. Now, the Core Ultra is faster, less power efficient, right? That means it consumes lesser amount of batteries. It's ultra fast and it's a premium product, and also it's smaller in comparison to the actual Intel Core i7, i5, i3, the old lineup of i processors. It's actually smaller, right? And significantly less uh, power hungry. So if you look at the data that they are given, they said it produces less heat, and it's really good for ultra thin laptops. So ultra thin laptops basically need to be power efficient, and also it should be heat tolerant. So less heat is better. Now, the way they got that is by using Boolean algebra, right? So if you look at this particular function over here, all right, this function over here, look how many steps were reduced, right? So it went from how many transistors are operating here. So you can just look at this. So there's a not, there is an and. Okay, so the not, the and gate, that's two. Here is a or gate, and here you have an and gate, another or gate, two not gates, and gate, or gate, and gate. That's 10 transistors to solve this problem. But guess what? In here, the final answer, I have only not or. I have only not and or. Yeah, that's it. I don't have anything else. So I went from 10 transistors over here. Okay, there are 10 transistors in here. Transistors. Okay, from 10 transistors, I came down to just 2 transistors. So if I draw this, it is not A goes into a OR gate. So that's A, B, and comes out as C. So your C is equal to A bar plus B. So you can see how easy it is, right? Oh, wait, hang on a minute. This is transistors because you didn't see it earlier. Transistors. Okay. Right. So those are 10 transistors drop down to just 2 transistors. So that's the advantage of these Boolean algebra. That's how you have the new Core Ultra Intel microprocessor that was just released. I think this year they released it, and it's a huge deal because it has built-in AI logic in as well, right? So next time when you see, Boolean algebra, you know the real value of Boolean algebra is to simplify the transistors that are there. Okay, right? So there are lots of examples that I have also given in the tutorial. Just go through it, and if you need anything, just give me a call, or you can message me or WhatsApp me, email me, or just comment in the section down there. Okay, thank you.